So that's one benefit of virtual memory. It lets us have these processes when we fork that start with the same virtual addresses but have isolated views of the memory. More generally, it simplifies memory management because every process, being isolated and having the illusion that it has all the memory, can use some consistent layout of that memory. Here's what the process's view of memory looks like for all Linux processes on x86 64. So the code is always going to be loaded somewhere close to, relatively speaking, close to memory address 0. Usually 4 with 5 zeros after it in hexadecimal or so. And then when you allocate memory, it can be written right after that. When you allocate memory with malloc. Meanwhile, the stack can be far away, so it doesn't collide with that heap, at the highest address that a user program can read. This address is 7 with 11 Fs after it. That turns out to be the midpoint in the virtual address space, because x86 64, despite using 64 bits to represent addresses, actually only has 48 bits that are meaningful addresses. The top 16 bits are constrained to be the same as the 17th highest bit. Another thing this picture shows you is that the space that a user program can use is only half of the virtual address space. The kernel reserves the other half. Right? If you this is 47 bits of space really for the user code, and so the kernel gets its own 47-bit space for whatever it wants to do. 47 bits is more than enough memory for a user process. Note that this drawing is not to scale, since the kernel virtual memory should be the same size as this half of the picture. And this gray area here is really vast, because it's the difference between this number plus however much data you have and this very large number here. So using virtual addresses, each process can take the standard view of memory when it actually gets mapped into different places in physical memory for different processes.